Imagine this, a star millions of times larger than our sun explodes. It's a cosmic fireworks display of unimaginable scale, a supernova. This isn't just any everyday event in the universe. Supernovae are the dramatic death throes of massive stars, marking the end of their life cycle in a blaze of glory. For a brief moment, a supernova can outshine an entire galaxy. This explosion is so bright we can even see it from Earth with the naked eye. But a supernova is more than just a light show. It's a cosmic factory, forging new elements and shaping the universe as we know it. Supernovae are crucial to our understanding of the universe. They help us measure cosmic distances and study the expansion of the cosmos. But beyond their scientific importance, supernovae have a profound philosophical implication. The iron in your blood, the calcium in your bones, the gold in your jewelry. They were all created billions of years ago in the heart of a dying star. We are, quite literally, stardust. The life cycle of a star is a journey of millions, sometimes billions of years. From the moment it is born in a nebula to its final explosive end, a star undergoes a series of transformations. In its youth, a star fuses hydrogen into helium, shining brightly in the cosmos. As it ages, it begins to fuse heavier elements, creating the building blocks of planets and life. Eventually, the star exhausts its fuel and expands into a red giant, a phase of immense size and luminosity. And then, in a final cataclysmic explosion, it becomes a supernova, scattering its enriched material across the universe. This material will eventually coalesce to form new stars, planets, and perhaps even life, continuing the cosmic cycle. So, the next time you look up at the night sky, remember that the light you see is not just from distant stars, but from the remnants of ancient supernovae, the echoes of cosmic creation. We are all part of this grand cosmic story, connected by the stardust that flows through our veins and the universe that surrounds us. To understand a supernova, we need to start with the life cycle of a star. This journey begins in the vast, cold expanse of space. Stars form from massive clouds of gas and dust, known as nebulae. These nebulae are the stellar nurseries of the universe. Gravity pulls this material inward, causing it to heat up and ignite nuclear fusion in the star's core. This fusion process is the engine that powers a star. For most of their lives, stars are in a delicate balance, a state known as the main sequence phase. The outward pressure from nuclear fusion battles against the inward pull of gravity, creating a stable equilibrium. But this balancing act can't last forever. Over time, the star exhausts its nuclear fuel. Stars are like cosmic furnaces, constantly burning through their fuel at an astonishing rate. For massive stars, this fuel is primarily hydrogen, the simplest and most abundant element in the universe. As hydrogen depletes, the star starts fusing heavier elements like helium and carbon, desperately trying to maintain its equilibrium. This process is a race against time. This process continues, creating progressively heavier elements until the star's core transforms into iron, the heaviest element a star can produce through fusion. Iron fusion, unlike other elements, doesn't release energy. It requires it, leading to an energy crisis within the star. This is where the balance tips. The outward pressure falters. Gravity wins, and the star's core can no longer support itself. And the star's core collapses in on itself, a dramatic and violent event. This collapse triggers a shock wave that rips through the star's outer layers, resulting in a cataclysmic explosion, a supernova. This spectacular event marks the end of the star's life and the beginning of a new chapter in the cosmos. Not all supernovae are created equal. These cosmic explosions, though similar in their spectacular displays, have different origins and characteristics. Astronomers have classified them into two main types, Type 1 and Type 2, based on their light curves and the elements detected in their spectra. This classification helps scientists understand the underlying processes that lead to these powerful events. Type 2 supernovae occur when massive stars, at least 8 times the mass of our Sun, reach the end of their lives. These stars have spent millions of years fusing elements in their cores, creating heavier and heavier elements until they can no longer sustain nuclear fusion. These stars have exhausted their nuclear fuel and undergo core collapse, as described earlier. The core collapses under its own gravity, leading to a catastrophic explosion that ejects the outer layers of the star into space. Type 1 supernovae, on the other hand, involve a different mechanism. They are not the result of a single massive star's death, but rather occur in binary star systems. In these systems, two stars orbit each other closely. One of these stars is a white dwarf, a dense, Earth-sized remnant of a Sun-like star that has already shed its outer layers. The white dwarf, though small, has an incredibly strong gravitational pull. It siphons material from its companion star, drawing in hydrogen and helium. As the white dwarf siphons material from its companion star, it gradually accumulates mass. When it reaches a critical mass, it becomes unstable. This instability triggers a runaway nuclear fusion reaction, resulting in a spectacular explosion. The white dwarf is completely destroyed in the process, leaving behind no remnant. This difference in origin leads to distinct observational signatures, allowing astronomers to differentiate between these two types of supernovae. By studying these signatures, scientists can learn more about the life cycles of stars and the dynamic processes that govern our universe.